All welcome back to the next session on polarization. So today I'm going to discuss how to produce circularly polarized and elliptically polarized light. Okay, so we already discussed what is meant by circular polarization and as well as elliptical polarization. Okay, so here we are going to discuss how we can produce it. Okay, now we can just revise those discussion, the circular polarization. So consider the light is propagating along z direction. Okay, and if the electric field is plane polarized, the direction of oscillation of electric field will be confined along one direction perpendicular to direction of propagation. Okay, suppose the direction of propagation along z direction. Okay, so propagation vector k, then electric field can oscillate along x direction or y direction or in between the x and y. Okay. Now suppose there are two mutual electric field is present all the time. Suppose some electric field is oscillating along x direction and another electric field oscillating along y direction. Then it is possible to get another kind of polarization, that is instead of linearly polarized light we can get circularly polarized or elliptically polarized light. Okay, so if this is situation, then while propagating the electromagnetic wave we may get the resultant vector of the electric field may rotate. So I can write the electric field along x direction as E0x some cos omega t minus kz, and Ey I can write E0y cos omega t minus kz plus phi. Okay, so where phi is the phase difference between Ex and Ey. So if the phase difference is 0, then there is no much of things to occur. So what would happen, you will get again a linear polarized light. Okay, so if the phase difference is 0, then both the x oscillation, y oscillation are oscillate together, and for in such cases we'll get the straight line. Okay, there is no new shape will come there, so you'll get linear polarized light only, and that happens for phi equal to 0 and as well as for phi equal to pi. Only difference is the direction of oscillation would be different. Okay, so even phi equal to 0 or phi equal to pi, what would be the direction of oscillation, that I can just draw it here. Okay, so remember the z is the direction of propagation. So suppose the light is coming towards you. Okay, so then I can draw this point be x and this would be y. If the light is coming towards you and if the total phase difference is 0 or pi, then the oscillation of the electric field would be like this. So if phase is 0, phi equal to 0, then the electric field would oscillate like this. And what about when phi equal to pi? When phi equal to pi, the oscillation of electric field would be like this. So it is nothing but the linear polarization. So remember, the light is coming towards you. Okay, the light is coming towards you, towards it, and whereas if the phase difference is 0, the phi is 0, then the direction of oscillation of electric field look like yellow while the light coming towards you, and if phi equal to pi, then the electric field would be oscillating like this blue vector. Okay, suppose if Ey is 0, what would happen? If Ey is 0, then the electric field will oscillate horizontally. The only x oscillation will be there. Okay, suppose if Ex is 0, then you will get only Ey. If Ex is 0, then only vertical oscillation would be present. Okay, so that is the case. So all such cases here is just an example of linearly polarized. Okay, so this is a case of linear polarization. So when you can get circular polarization, so circular polarization is possible only if phi equal to pi by 2 or 3 pi by 2. Okay, when phi equal to pi by 2 or 3 pi by 2, then there is a possibility of circular polarization. So if phi equal to pi by 2 or 3 pi by 2, then what would be the direction of oscillation of the electric field or electric vector? Okay, so again I can draw the x and y direction here. This is your x and y. The light is coming towards you. So if the light is coming towards you, then the electric field vector or the tip of the electric field would rotate. So the tip of the electric field will rotate while it coming towards you. At some time the electric field vector will be like this. After some time the electric field will come like this. The electric field vector will come like this. So the electric field vector will start rotating with time. So such kind of polarization is called the circular polarization. Okay, now earlier what happens is the electric field oscillation is directed only along one direction, but here the electric field oscillation changes with time. When it propagates forward, the direction of electric field changes. It rotates with time and rotates with propagation. So such kind of polarization is called circular polarization, and circular polarization will happen when phi equal to pi by 2. That is, if the phase difference between the horizontal and vertical oscillation, the x and y oscillation, is pi by 2 or 3 pi by 2, then this kind of thing happen. And again you have to remember one more thing, this length. Okay, so I will just draw it. So this length would be nothing but E0x, and this vertical length is given by E0y. So you will get a circle. You will get a circular polarization only if E0x equal to E0y. That is, if the amplitude along x direction and y direction are same, then you will get circular polarization. And when you will get elliptical polarization, okay, so obviously you will get elliptical polarization if the amplitudes are not same. If E0x is not equal to E0y, then you will get elliptical polarization. So that means you know to get the elliptical or circular polarization, the first thing is there should be some phase difference between the x oscillation and y oscillation. Okay, the x direction electric field and y direction electric field, there must be a phase difference of pi by 2 or 3 pi by 2. That's the one first thing. And in order to get circular polarization, the amplitudes must be same, and for elliptical polarization, amplitude must be different. Okay, so this is the theory. I think we have already discussed it, this theory, the circular polarization and elliptical polarization. Now we can discuss how we can produce it. Now in order to produce such light, we can use the quarter wave plate, because we know that the quarter wave plate can produce a path difference of lambda by 2, and the phase difference pi by 2. Okay, the phase difference of pi by 2 phase difference is equivalent to lambda by 4 path difference. So in order to produce a pi by 2 phase difference, I think only a quarter wave plate is enough. Okay, so then we can discuss the arrangement, how to produce this circular polarized light. Okay, now first of all, how can you produce a linearly polarized light? How can you produce a linearly polarized light? Okay, so the linearly polarized light you can produce by just using a polarizer. Okay, suppose the light is propagating along this particular direction, and you have an unpolarized light with you. Okay, so if this unpolarized light incident on a polarizer, suppose this is a polarizer, its path, and the polarization axis. Okay, let this would be the polarization axis. And what would happen after this path axis or after this polarizer? We'll get only one type of oscillation. We get only vertical oscillation. Okay, so we can convert an unpolarized light into a polarized light just using a polarizer. Okay, so there are many types of polarizer as we discussed. One example is an equal prism is a polarizer, and what is the another example? The Polaroid is a polarizer. Polaroid sheet is a polarizer. Okay, so there can be many such examples for the polarizers. So just using a polarizer, you can polarize an unpolarized light. Okay, so there is a production of linear polarized light. How to produce circular polarized light? Okay, so for the circular polarized light or elliptical polarized light, it is slightly more complicated. Okay, so I think better I can use this picture. Okay, so the production of circularly polarized or elliptically polarized light. So at a time we can produce only one, either circular polarized or elliptically polarized. Okay, so now this light is moving. Okay, then okay, so this since it is passed through a polarizer, we already got a linear polarized light. Now we are passing this linear polarized light through a quarter wave plate. Now quarter wave plate can produce two lights, an ordinary light and extraordinary light, and there can be a path difference of lambda by 4 between them. Okay, now there is one more point. Okay, so here there is a two axes. One is the path axis for ordinary light and another one is the path axis for extraordinary light, because the ordinary light and extraordinary light are both are linearly polarized in mutually perpendicular direction. Okay, suppose your the path axis or the optic axis are like this. The optic axis corresponding to the ordinary light. Then what would happen? If this is the case, then after passing through the quarter wave plate, there will not be any change of polarization, because it will pass only ordinary ray. There cannot be production of extraordinary ray, because this axis is the path axis of ordinary ray, and after this quarter wave plate, you will get only one ray. Again, you will get a linear polarized light. So then how can you produce circular polarized light? How? Okay, so for that what I have to do is we have to rotate this quarter wave plate by 45 degree. If you rotate the quarter wave plate by 45 degree, then what would happen? If you rotate the quarter wave plate by 45 degree, then this ordinary path axis will rotate by 45 degree. Okay, and now your incident light, the incident light to the quarter wave plate is linearly polarized. Now this can be resolved into two. One is the light parallel to the path axis and the light perpendicular to the path axis. Okay, but I will use another color. The light parallel to the path axis and the light perpendicular to the path axis. So that means here you will get two lights. Okay, so you will get two lights. One is the light parallel to the path x, that means you will get an ordinary light. So ordinary light would be oscillating like this. Ordinary light would be oscillating like this, and extraordinary light would be oscillating perpendicular to it. Okay, and there would be some phase difference because since this is a quarter wave plate, there would be a phase difference of pi by 2 between them, or a path difference of lambda by 4 between them. Okay, so you can produce, so what happens is here you are getting two rays, ordinary ray and extraordinary ray, so which are mutually perpendicular. Okay, so I think it will lead to slight confusion, so better I will change the explanation. So instead of rotating the quarter wave plate, the better thing is you can rotate the polarizer. I think that will give some better understanding for you. Okay, so anyhow I will complete it, then we'll go to the next explanation. Okay, so here we get the phase difference of pi by 2 or path difference of lambda by 4. So then what you can get is, here you can get a circularly polarized light. Okay, then how can you get elliptically polarized light? Elliptically polarized light, if the rotation is not equal to 45 degree, then you will get elliptically polarized light. Okay, so for a better understanding, I will do another explanation. Okay, so consider again light is propagating like this. Okay, and you have a polarizer first. A polarizer with the path axis, so it will convert an unpolarized light into a polarized light, and after that we have a quarter wave plate here. Quarter wave plate with a path axis. Okay, then what would happen is, if this is a case, then there will not be any change. You will get only a plain polarized light. Okay, no change. If the incident light, the oscillation of the incident light is parallel to the path axis of the quarter wave plate, then no change will occur in the case of polarization. But the change would occur if the incident light, or if the oscillation of the incident light is making some angle with the path axis. So in order to produce circular polarized or elliptically polarized light, the oscillation of electric field of incident linear polarized light must make an angle theta with the optic axis of quarter wave plate. Okay, so for that, better thing is I can just rotate the polarizer. If you rotate the polarizer, what would happen? The oscillation of electric field would change. The electric field would be oscillating in some other direction. Okay, so then here the incident light, the electric field would be like this. Now when it passing through this quarter wave plate, you will get two rays, the ordinary ray and extraordinary ray, and that will make a phase difference of pi by 2 or path difference of lambda by 4. Okay, so that is the case. So then you'll get two field here. One is electric field oscillating along x direction. Suppose this direction of propagation is z. Okay, then this direction I can put it as y. This direction as x. So x, y, z. So the x direction would be E0 x cos omega t minus kz, and Ey would be E0 y cos omega t minus kz plus pi by 2. So obviously we'll get circular polarized or elliptically polarized after this. Okay, now what about E0x and E0y? So the magnitude of E0x and E0y depending upon this angle. Okay, so if you look at this, there is some angle, angle between the path axis and the oscillation of electric field. Okay, so I will draw it more clearly. Is your blue line? Here it is your electric field oscillation, and the angle between them, this angle is theta. So therefore the E0x would be the E0 sin theta, and E0 would be E0 cos theta. So when theta equal to 45 degree, then E0x must be equal to E0y. So that would give to circular polarized light. If theta is not equal to 45 degree, then E0x not equal to E0y, and that will lead to elliptically polarized. So okay, remember this theta should not be 0 or it should not be 180 degree also. Okay, so that's it. Okay, so then I think this with this is very clear. This gives a clear understanding of how we can produce a circular polarized and elliptically polarized light. So okay, all so with this I think we have finished the discussion of the production of circular polarized and elliptical polarized light and even the linear polarized light. So next is the analysis of the polarized light. I am leaving to you so that you can write as an assignment. That is how we can analyze a circular, or how we can distinguish a light, whether the incoming light is circular or whether the incoming light is elliptical or whether it is linear or polarized. Okay, so there is some method to it. So that analysis part I am leaving to as an assignment to you. So all of you has to submit that assignment maybe in 1 week of time. Okay, so that I will post in your Google Classroom. Okay, so with this we have finished the in-depth topic on polarization. So next we will discuss certain problems, the tutorials on this topic. Okay, so thank you for watching. So we'll see in the next session as tutorial. Bye.